Hello. In the previous lecture, in the previous video, hello. In the previous video, we defined an operation on the set of left cosets of a normal subgroup. In fact, we defined a normal subgroup to be a subgroup where the left cosets are equal to the right cosets as sets. So in a sense that xn equals to nx for every element x in the group G. For this type of subgroups that we call normal subgroups, we showed that xn dot yn equal to xyn is a well-defined operation on the set of left cosets of the subgroup N. Essentially, the part one of this proposition we have already proved. Now we want to use that operation and show that G over N becomes a group with respect to this binary operation. Moreover, if I send X to the coset that X represents, if I define P of X to be Xn, then this is a surjective group homomorphism from G to the quotient of G by N, or the factor group of G by N. And kernel of this group homomorphism is simply N. So these are four parts of this proposition, this important proposition. All together, we call G over N. And so we get a factor group. What happened? So all together, we end up getting this group that we call the factor group of G by N, or the quotient of G by N. And we also get this natural quotient map from G to the quotient of G by N, which sends X to the coset that X represents. And this is a surjective group homomorphism whose kernel is N. These are the important parts of this proposition. Of course, without part one, we cannot even talk about a group, because for a group, we do need an operation. Let's go to the proof. Similar to the case of group of integers modulo n, the hard part is actually to show that the operation is well defined. And the rest of the proof, the rest of the claims immediately follow from the fact that G itself is a group, and at the end of the day, we are doing operation within the group because we are picking two arbitrary representatives of these cosets, and then we are doing group operation with respect to these representatives. So to speak, I can say that we are doing operation within the group and decorate them with N. So all the properties of the group G should pass on to the factor group, to the quotient group of G by N. Okay, but let's make it precise. As I have indicated, part one, meaning the fact that this dot product, and this product is indeed well defined, had been done before. Now let's check why it is a group with respect to this operation. We start by checking why we have a neutral element. Of course, we have to take the coset that has the neutral element of the group G in it, because we want to use properties of the group G. So I look at the coset that's represented by E sub G, and then when I multiply it by an arbitrary left coset, I need to multiply the coset representatives, that's the neutral element of the group, times X, and then the coset that this element gives me. But remember, E sub G times X is X, and therefore we get the coset that's represented by X. Similarly, I take this coset and multiply it from right by this coset. Again, E sub G is the neutral element of the group. Therefore, X times E sub G gives me back X, and I'm getting the coset that I have started with. So it is clear that this is a neutral element of this operation. And notice that the coset that the neutral element represents, this set, is simply n. So as a set, it's basically n. Therefore, the coset n is the neutral element of the factor group of G by n. Now, how about the inverse? Again, we have to take the inverse inside G and decorate it by n. That means we need to pick the coset that's represented by X inverse in order to get the inverse of the coset that's represented by X. So I take X inverse n and I multiply it by Xn. The way that we define this multiplication is simply by multiplying these coset representatives and then taking the coset that that product represents. So X inverse times X, and then the coset that X inverse times X represents is this. But remember, X inverse X is the neutral element, and this is precisely the neutral element of the factor G over n with respect to this multiplication. And similarly, if I multiply Xn this time from left by X inverse n, I end up getting the same result. So that means we do have an inverse. Every element has an inverse. Finally, let's check why this operation is associative. Similar as before, we have to use the fact that multiplication of the group G is associative. So we write the multiplication that we are interested in, and notice that we are essentially doing the multiplication inside G and decorate it by n, so to speak. So Xn dot Yn is simply Xyn, and then dot Zn, that means I'm multiplying Xy by Z and then taking the coset. Now, I want to show that this, I am allowed to switch the order of parentheses and write this as Xn dot parentheses Yn dot Zn. Now we do the same as before, and we write this down as Yzn, and then Xn times this, and that means X, Yz, and then the coset that that element represents. But remember, the group G itself, the multiplication in the group G is associative. Therefore, this element is equal to this element. In particular, they give me the same cosets. So these cosets are equal, and that would imply associativity of the operation in G over n. Okay, so far we checked that it is a group. Let's see why P is a groupomorphism. That's rather easy. That's essentially saying that when I want to multiply two cosets, I simply multiply coset representatives and then take the coset. So that's P of xy, and therefore P is a groupomorphism. This P we call the natural quotient map. Clearly it is surjective because every element in G over n is of the form Xn, and therefore it is of the form P of x. So it is a surjective groupomorphism. So let me write this down as well. So for every element of codomain, is of the form xn, and that is equal to P of x. That means P is surjective. So that implies surjectivity of P. Now let's try to understand kernel of P. That's the last part of the proposition. X belongs to the kernel of P precisely when P of X is the neutral element of the codomain. But the neutral element of the codomain is the coset that's represented by the neutral element. So xn and P of X is xn. So xn is supposed to be the neutral element, the coset that's represented by the neutral element. But remember, two cosets are equal, two left cosets xn and yn are equal precisely when y inverse x or x inverse y belong to n. So now if I apply this for this equality, I deduce that the neutral element inverse times x should belong to the subgroup capital N. But this is the neutral element, I can drop this. So therefore this claim is equivalent to saying that x belongs to N. So x is in the kernel of P exactly when x is inside N. That means kernel of P is simply N, as we wanted to show. Okay, so now we have this mechanism to factor a group by a normal subgroup and get a new group out of that. Let's see some examples, basic examples, and then we see machinery of understanding the group structure of factor groups. But let's start with this easy example of the alternating group inside the symmetric group. So we want to show the alternating group is a normal subgroup of the symmetric group, and we want to understand the factor group or the quotient of S sub n by A sub n when n is at least 2. Otherwise, S sub 1 has only one element. That's not interesting. So when I say I want to write down the multiplication table, I'm essentially telling you that I want to understand the group structure of this group. Let's start by showing why A sub n is a normal subgroup. What is A sub n? A sub n is the kernel of the sine function. Alternatively, I can say it is the set of all even permutations. But for the purpose of this example, it's better to think about it as the kernel of the sine function. Remember, we have this sine function from the permutations, from the symmetric group to the group consisting of only two elements, 1 and -1, under multiplication. And we assigned 1 to even permutations and -1 to odd permutations. And we discussed that this sine function is a groupomorphism, and the way that we defined it implies that kernel of sine function is precisely the alternating group. Now, we have proved that kernel of every group homomorphism is a normal subgroup. From that, we can deduce that the alternating group is a normal subgroup of the symmetric group. I could also argue that we've seen the index of A sub n inside S sub n to be 2, and we proved that every subgroup of index 2 is normal. So these are two different ways of proving that alternating group is a normal subgroup of the symmetric group. Okay, so where we showed that the index of A sub n in S sub n is 2, in fact, we proved that every coset that's represented by an even permutation is simply A sub n, is simply the coset that's represented by the neutral element, and every coset that's represented by an odd permutation can be represented by a transposition like 1, 2. So this we've seen before, that the set of right cosets of A sub n has only two elements. One of them is A sub n, the coset that's represented by the neutral element, and the other one is the coset that's represented by the transposition 1, 2. Because A sub n is a normal subgroup, the set of left cosets is equal to the set of right cosets, and I can simply bring this to the other side because A sub n is a normal subgroup. So the set of left cosets of A sub n consists of two elements. One of them is the coset that's represented by the neutral element, and the other one is the coset that's represented by the transposition 1, 2. Now I want to write down the multiplication table of this group. So I write down those elements, A sub n, and the coset that's represented by the transposition 1, 2, and I write them in the column as well. Now, A sub n times A sub n, I need to multiply the neutral element, the coset representatives. I end up getting the neutral element, so I end up getting A sub n. To multiply these two, I have to multiply the coset representatives. I end up getting the transposition 1, 2, and the coset that transposition represents. Similarly, I get the same result over here. Finally, to understand this part, I need to multiply this transposition by this one. But a transposition squared is identity, so we get the coset that's represented by identity, and that is A sub n. Now let me write down the multiplication table of this group as well. The multiplication table of that group, I write down, you see, A sub n was the identity, so I put the identity of the codomain purposely besides A sub n, and the other element besides the coset that's represented by 1, 2. I do the same on the column. Now I follow multiplication of the codomain. 1 times 1 is 1, 1 times -1 is -1. -1 times 1 is -1, and -1 times 1 is 1. Now you see that if I send A sub n to 1 and this coset to -1, then all multiplications match up. That means what? That means sending A sub n to 1 and the coset that's represented by the transposition 1 to -1 is a group isomorphism from the factor group, from the quotient of S sub n by A sub n to the group, to the codomain, to the group that contains 1 and -1. Next, we want to generalize this. This is not a particular fact only for the alternating group. This is an important fact in group theory, and we call this, so in this course we call it fundamental theorem of groupomorphisms, but the more common name is the first isomorphism theorem, because there are second and third isomorphism theorems as well, but those ones we do not discuss, and they are essentially corollaries of the first isomorphism theorem. And another reason is that we have similar results in ring theory, in module theory. And so in 103b, you will be learning about the first isomorphism theorem for rings, for system of numbers that have two operations, addition and multiplication. Okay, but let's continue with what the statement is. What is this first isomorphism theorem? Suppose I give you two groups, one of them with a dot operation and the other one with a star operation, and I give you a group homomorphism F from G to H. So it's a group homomorphism. We have already seen and discussed that kernel of every group homomorphism is a normal subgroup of domain. An image of every group homomorphism is a subgroup of codomain. Now, the second part is the important part of this theorem. It says, okay, now that kernel of F is a normal subgroup, I can talk about the quotient group or the factor group of G by the kernel of F. So let's take the quotient of G by the kernel of F. Now I'm going to give you an isomorphism from this quotient group to image of F. So claim is that G modeled by kernel of F is isomorphic to image of F. And in fact, we can also say what that isomorphism is. I mean, it's not a unique one, but we can give an isomorphism from this quotient group to the image of F. So what is that F bar? F bar sends the coset that's represented by X to what F does to the coset representative. So if I pick a coset representative X and I apply F to that coset representative, then this gives us a well-defined isomorphism from the factor group G over kernel of F to the image of F. So that's the claim, that this is a well-defined group isomorphism from this factor group to image of F. Again, let me emphasize that this is an extremely important result. You will be using this later when you take 103B and you study ring theory. This result will be used again. Okay, so again, we have already discussed that the kernel of every group homomorphism is a normal subgroup of domain, and image of every group homomorphism is a subgroup of codomain. Now, we want to show that F bar is well defined. Again, let's think about what the issue is. The issue is that here I'm giving you a coset. This coset is a set, but then I am picking one element out of this set and telling you how to compute this only based on that element. So it's like having a community and saying that F bar, saying that all the elements, all the members of this community have the same property under F. So it's kind of a stereotyping, and we want to say that this one is okay. They do have the same property from F point of view. Okay, so let's see why. Let's formulate it mathematically and try to prove it. Again, I'm saying that if I pick two representatives from this community, if X times kernel of F is equal to X prime times kernel of F, then from F point of view, I do get the same values. So they do have the same property with respect to F. So F of X equals to F of X prime. And that is what we have to address. Okay, so let's start with the hypothesis. Knowing that these two left cosets are equal is equivalent to saying that inverse of X prime times X belongs to the kernel of F. So it is equivalent, in fact, to saying that X inverse times X prime or X prime inverse times X belongs to the kernel of F. Okay, so far so good. But what does that mean? What is kernel of F? Kernel of F consists of all those elements of the code of the domain that are mapped to the neutral element of the codomain. So we say it is the set of, it is the 5 over the neutral element. So if this is G and this is my H, and I give you this element, the neutral element of H, we are asking what are these elements that are on top of the neutral element. So that is kernel of F. Okay. So knowing that X inverse X prime belongs to the kernel of F, I can deduce that when I apply F to this element, I end up getting the neutral element of the codomain. Now, F is a groupomorphism. That means it preserves the operation. So F of product is products of F's, but here product, the operation of the codomain is denoted by star. So I have to change this dot to star. And we have also showed that F of inverse is inverse of F. So F of X inverse is F of X, and then we take the inverse. So altogether we get that this is the same as F of X inverse star F of X prime. And that is supposed to be the neutral element of the codomain. Multiplying both sides by F of X, this disappears. I get F of X prime on the left-hand side. And when I multiply F of X by the neutral element, I end up getting F of X. And that's exactly what we wanted to show. We end up getting that F of X prime is equal to F of X. And that is exactly the implication we were seeking. So F is indeed well defined in a sense that the rule that we are saying does not depend on the choice of a coset representative. But we also need to be a bit careful because I'm changing the codomain as well. I need to say that I will be landing in the new codomain. And this is the case because what I'm getting, no matter what the element that I'm applying to is, what I'm going to get does belong to the image of F. So now we have checked all the possible issues and we showed that F bar is well defined. Again, because F bar of a left coset is F of X and that does belong to the new codomain, we deduce that F bar is a well-defined function. Now that it's a well-defined function, I am going to check that it is a group homomorphism. Okay, so I feed it product of two cosets, X kernel F times Y kernel F. The way that we define this multiplication of cosets is by multiplying the coset representatives and taking the coset that xy represents. So this multiplication is equal to the coset that xy represents modulo kernel of F. So that means I need to apply F bar to this coset. But the way that we defined F bar is as follows, that F bar of a coset is equal to F of the coset representative or a coset representative. So this is the same as F of a coset representative, and X times Y is a coset representative of this coset. Now, F is a groupomorphism. Therefore, Fxy is F of X star F of Y. But remember, F of X is F bar of this coset. And F of Y is F bar of the coset that's represented by Y. Altogether, we deduce that F bar of product of cosets is product of F bars, and therefore F bar is a group homomorphism. Okay, next let's check why F bar is injective. That means when I give it two cosets and I happen to get the same value, then those two cosets have to be equal. So if F bar of X kernel F is equal to F bar of Y kernel F, I have to be able to deduce that X kernel F is equal to Y kernel F. Okay, let's start with the hypothesis. We are told that this is equal to that one. By definition, F bar of this coset is F of the representative, and F bar of this coset is F of the coset representative. Now, we are going to multiply both sides by inverse of F of Y from left, and I end up getting that it is F of Y inverse star F of X is equal to, and as I multiply by inverse of this element, I end up getting the neutral element of the codomain. So this product is equal to the neutral element of the codomain. Now, we know that F is a group homomorphism. Therefore, this product is simply F of Y inverse X. So F of Y inverse X is supposed to be the neutral element of codomain. By definition, that means Y inverse X is in the kernel of F. Again, remember, two cosets Xn is equal to Yn precisely when Y inverse X is inside N. This is an important result. This is true for every subgroup, not necessarily normal. Now we are applying that over here. So I know that Y inverse X belongs to this subgroup, from which I can deduce that the coset that's represented by X is equal to the coset that's represented by Y. The left coset that's represented by these elements are the same. And that's exactly what I wanted to show. So starting with this hypothesis, I end up showing that they are the same cosets, and that means that F bar is injective. Now let's argue why F bar is surjective. Okay, so I pick something in the codomain. Codomain of F bar is image of F. So that means I have to pick some element in the image of F. Saying that Z is inside image of F means that Z is F of X for some X in the domain of F. But remember, F of X is equal to F bar of the coset that's represented by X. In particular, so now that I know Z is F bar of something, I can deduce that it is in the image of F bar. That means F bar can attain everything inside its codomain, which means F bar is surjective. We showed that F bar is well defined. We showed that F bar is a group homomorphism. We discussed that it is injective and surjective, and therefore F bar is an isomorphism from G over kernel of F to its image. Okay, so let's see some examples on how we can use the first isomorphism theorem. For instance, we want to show that the factor group of R over Z, I'm thinking about the set of real numbers under addition and the set of integers under addition. The set of integers is, of course, a subgroup of the set of real numbers. And because these are abelian, every subgroup is normal. So it does make sense to talk about R over Z. And my claim is that this is isomorphic to the unit circle under multiplication. So I'm thinking about a circle as points in the complex plane, all those complex numbers that have norm 1. And we know as I multiply two complex numbers that have norm 1, I'm going to get another complex number that has norm 1, and inverse of a complex number that has norm 1 is going to be another complex number that has norm 1. We have discussed that S1 under multiplication is a subgroup of non-zero complex numbers under multiplication. Now, claim is that R over Z, this factor group, is isomorphic to S1. Okay, how can we do this? So the general rule is that whenever I give you a factor group and a target group, it's better to start from the numerator and think about a groupomorphism from the numerator to the other side, hopefully surjective, and make it in a way that the kernel of that groupomorphism turns out would be the denominator of this quotient group. If you manage to find such a groupomorphism, then applying the first isomorphism theorem or the fundamental theorem of groupomorphisms, you can get the desired isomorphism. In this case, we have already seen a groupomorphism from the set of the group of real numbers to the unit disk, with the property that this groupomorphism is surjective and the kernel of this groupomorphism is precisely the group of integers. Let me recall what that groupomorphism is. So let's consider e to power 2 pi I x, where x is a real number. We have seen that this function is a groupomorphism. Its kernel is the set of integers, and its image is the entire circle. Let me quickly go over the argument why all these three properties hold. Let's start with groupomorphism. That is the easiest of all. So I have that this times this equals to e to power summation of the powers, and I can factor out 2 pi I, and I end up getting that fx plus y is equal to f of x times f of y. And that's exactly what we wanted to show. So f is a groupomorphism. Now let's see why kernel of f is the set of integers. So suppose f of x is 1. That happens if and only if e to power 2 pi I x is 1. Remember, e to power I theta, so let me write it over here. So using a circle, this is my unit disk. So when I give you theta, then in this unit disk, e to power I theta, this is Euler's equation, e to power I theta gives us this point. That's cosine of theta plus I sine of theta. So in particular, if I want to land at 1, this theta needs to be an integer multiple of 2 pi. That means e to power 2 pi I x is 1 if and only if x is an integer, because we want to make sure that 2 pi x is an integer multiple of 2 pi. That means x should be an integer. So this gives us that kernel of f equals to z. And this picture shows us that indeed it is surjective, because everything that I give you, every z inside S1, z is of the form e to power I theta for some theta, and that implies that z is f of theta divided by 2 pi. These things we had discussed earlier, but I wanted to make sure that we know how to prove all these three properties. Now that I understand kernel of f and I understand image of f, I can apply the first isomorphism theorem. By the first isomorphism theorem, I know that R over kernel of f is isomorphic to the image of f Now, kernel of F is Z, and image of F is the entire S1. So we get that there is this isomorphism from the quotient of R by the kernel, which is Z, to the image of F, which is S1. And in fact, the first isomorphism theorem also tells us what an isomorphism is. I mean, it gives us an isomorphism from the quotient of R by Z to the image of F. And essentially, we apply F to a coset representative of X plus Z, which is X. So the first isomorphism theorem tells us that this map F bar is a well-defined group isomorphism. In particular, we get that the quotient of R by Z is isomorphic to S1. Let's see another example. Again, what I'm doing right now is that I'm going through some of these group homomorphisms that we have discussed earlier, discussed their kernels, discussed their image, and I'm applying the first isomorphism theorem to those group homomorphisms. This time I want to show that the set of units of complex numbers, which is essentially every non-zero element in complex numbers under multiplication. And then I want to look at quotient of that by the unit circle. And my claim is that this quotient is isomorphic to positive real numbers under multiplication. Okay, so as I said in the previous example, whenever you want to understand quotient of a group and you want to show that quotient of this group is isomorphic to another group, it's better to start with the numerator and try to think of a group homomorphism from the numerator to the other side, and try to think a group homomorphism that has denominator as its kernel. Now, I want to think about a group homomorphism from non-zero complex numbers to positive real numbers, where over the units, if complex number has norm 1, I'm supposed to get 1. Okay, if complex number has norm 1, I'm supposed to get 1. How about norm? Norm of a complex number that has norm 1 is 1. Okay, so let's start with that. I look at n. Given a non-zero complex number, I take its norm, and because it's non-zero, norm of a non-zero complex number is definitely a positive real number. So n of z equal to norm of z or magnitude of z does give me a positive real number. And we have seen that you have seen this earlier when you learned about complex numbers as well, that magnitude of product is product of magnitudes, and that implies that n is a group homomorphism. So it's a group homomorphism, and it is also surjective because magnitude of a positive real number is itself. Therefore, this n is a surjective group homomorphism. Its image is the entire R plus. Now we understood its image. We understood its group homomorphism. How about its kernel? So by definition, Z belongs to the kernel of n precisely when its norm is 1. That means Z is in the kernel precisely when, exactly when Z is in the circle, unit circle centered at the origin in S1. Therefore, kernel of n is S1. Okay, we understood its image, it's R plus. We understood its kernel, it's S1. Now I'm in the good place to use the first isomorphism theorem. By the first isomorphism theorem, domain modeled by kernel of n is isomorphic to image of n. Now, kernel of n is S1, and image of n is R plus because it's surjective. So altogether we get a claim that the set of non-zero complex numbers modeled by the group of units is isomorphic, modeled by unit circle is isomorphic to R plus. Okay, so the next example we have already seen before when we discussed isomorphism of groups in general, but here I want to give you an alternative way of proving it. So suppose G is a cyclic group of order m. So it is generated by an element G, small g, and we are told that it has m elements. In that case, I want to show that G is isomorphic to Z sub m, the set of integers modulo m. Again, we have seen this statement before that up to isomorphism, cyclic groups of order m are unique. All of them are isomorphic to Z sub m. But now I want to give you an alternative method of proving this statement. Both of the arguments starts with this fact that I have a groupomorphism from Z to an arbitrary group G, sending integer n to G raised to power n. Now, knowing that this group is generated by the element G, I deduce that F is surjective because all the elements of a cyclic group generated by G are of the form G raised to some integer power. So F is surjective. Now we understood its image. Now let's focus on the kernel of F. What can we say about the kernel of F? Remember, something is in the kernel of F precisely when f of k is the neutral element of the codomain, and that means g to the k is supposed to be the neutral element of the codomain. But here it comes definition of order. Remember, we have proved that cardinality or order of a cyclic group is equal to the order of the element G. Knowing that cardinality of the group is m, we deduce that order of this element is m. And that means an integer power of this element is the neutral element precisely when the order of the element divides k, m divides k. Altogether, we deduce that k is in the kernel precisely when it's a multiple of m. So kernel of f is mz, is the subgroup of z consisting of multiples of m, and that one we denote by mz. Now, we understood the kernel of f, that's mz. We understood the image of f, that's the entire cyclic group G. And therefore, by the first isomorphism theorem, domain modeled by the kernel of f is isomorphic to image of f. Kernel of f is mz. Image of f is the entire cyclic group G. So Z, the factor group of Z by mz is isomorphic to G. Now, what is the factor group of Z by mz? The factor group of Z by mz, every element of this is a left coset. Every element looks like this, x plus mz. This is the set, or this is the set of this arithmetic progression. And this is precisely the residue class of x modulo m. So we see that the set of all the left cosets of mz is precisely the set of all the residue classes modulo m. Therefore, the quotient of z by mz is equal to the set of the integers modulo m. And they are the same groups. the same way that we add these elements. That's exactly how we add these ones, by adding their representatives. Therefore, the group of integers modulo m is isomorphic to the cyclic group G. Next, we are going to discuss Chinese remainder theorem. You have already seen this as part of your homework assignment. In fact, you have seen a bit more than what we are going to show in this example. But the method that was suggested in your homework assignment is different from the way that I'm going to present right now. Okay, so what is the statement? Starting with two positive integers that are coprime, z sub mn is isomorphic to the Cartesian product of z sub m and z sub n. Remember, when I give you two groups, then their Cartesian product form a new group essentially by multiplying, or in this case, adding component-wise. So if I give you two elements here, so let's say a sub m and a prime sub n, and when I want to add this to another element, I do it component-wise. I add the first component to the first component and the second component to the second component. And this way we end up getting a group. Check on your own why this is in fact a group. It's easy. Okay, so our claim is that z sub mn is isomorphic to z sub m cross z sub n. As we have mentioned up here, the set of integers modulo mn is the factor group of z by the subgroup mnz. So what we are asking here is to show that the factor group of z by mnz is supposed to be isomorphic to the other side. Now we are in the realm of this general recipe. Whenever I want to show a factor group is isomorphic to another group, it's better to start with the numerator and a groupomorphism from the numerator to the other side. And then we hope that kernel of this groupomorphism is the denominator, and therefore by applying the first isomorphism theorem, we get the desired result. Okay, so now what is this groupomorphism that I want to get from Z to this product? Okay, so if I want to give you a groupomorphism from Z to the product, that means I need to give you two information. I give you an integer, and then you have to give me something inside Z sub n and something inside Z sub n. Okay, I give you A, you have to give me something inside Z sub n. Why not in the residue class of A modulo m? So I give you the residue class of A mod m and the residue class of A mod n. That is my function f. My claim is that this function is a groupomorphism. Okay, let's check why this is the case. F of A plus B for integers A and B is the residue class of A plus B modulo m, comma, the residue class of A plus B modulo n. But this residue class is the same as summation of the residue classes of A and B modulo m. So f of A plus B is residue class of A mod m plus residue class of B mod m, comma, residue class of A mod n plus residue class of B mod n. The way that we add pairs of elements is by adding component-wise, so I can separate them now. I can put this guy here and this guy here. So if I want to add this pair to this one, I need to add the first components, and that's exactly here. And I need to add the second components, and that's exactly here. So I get the equality that we have over here. And remember, this is f of a, and this one is f of b. All together, we end up getting that f is a group homomorphism. So now I'm getting a group homomorphism from Z to Z sub m cross Z sub n. I want to understand its image and kernel. Let's start understanding the kernel. Often it's easier to understand kernel. Okay, so A belongs to the kernel precisely when it is sent to the neutral element of the codomain. But neutral element of codomain, this means when I add, I don't change it. That means both of the components need to be zero. So f of a is supposed to be 0, 0. What does that mean? F of a, the first component of f of a, is the residue class of a mod m. And that's supposed to be the residue class of 0 mod m. And the second component of f of a is the residue class of a mod n. And that is supposed to be the residue class of 0 mod n. This means m divides a. And this one means n divides a. Now, remember, so this means that a is a common multiple and common multiple of mn, one can show, because m and n are co-prime, so when it's a common multiple, that from here we can deduce that the least common multiple of AB is divisible by m. So alternatively, I can, okay, so let's continue like this. So the least common multiple divides A. And because they are co-prime, the least common multiple is the product of the elements. We have seen this using Euclid's lemma. Let me quickly go over the argument on how we can show this, this result. Okay, so let me quickly write it over here. Since m divides a, we deduce that a is m times k for some integer k. Now, because n divides a, we deduce that n divides mk. Now remember, GCD of m and n is 1, and therefore, by Euclid's lemma, n divides k. So k itself is a multiple of n. Now I can plug in back and I can plug it in over here and I get that A is m times n times L. Therefore, A is a multiple of mn. So these are two different ways of arguing why we have this implication. But in any case, because m and n are coprime and m divides n, A and n divides A, we can deduce that mn divides A. So A belongs to the kernel of F precisely when it's a multiple of mn. That means kernel of F is equal to multiples of mn, and it's m and z. Now we understand kernel of F. We haven't understood image of F, but But let's go to the first isomorphism theorem anyway. By the first isomorphism theorem, Z over the kernel of F is isomorphic to the image of F. Kernel of F we understood, that is M and Z. So Z over M and Z is isomorphic to image of F. We have discussed that this factor group is indeed equal to the set of integers modulo Mn. And because I have this isomorphism, we deduce that image of F has Mn elements. Okay, now let's think about it. Image of F is a subgroup of the codomain, which is Z sub M cross Z sub N. And it has Mn elements, but the codomain itself has Mn elements. So we cannot miss any of it. If we miss at least one element, then image of F cannot have Mn elements. We'll have strictly less than Mn elements. From these three facts, the fact that this is a subgroup of Z sub M cross Z sub N, it has Mn elements, and Z sub M cross Z sub N itself has Mn elements, we deduce equality. We deduce that image of F is the entire Z sub M cross Z sub N. So we had already discussed that Z sub Mn is isomorphic to the image. Now we showed that image is equal to Z sub M cross Z sub N. We deduce that Z sub Mn is isomorphic to the Cartesian product of Z sub M cross Z sub N. This is called the Chinese remainder theorem. Let's finish these examples and this video about the first isomorphism theorem with a non-abelian example. Most of the examples that we have discussed so far were abelian groups, with the exception of the symmetric group modding out by the alternating group. In this example, we are going to introduce a new group. We haven't seen this group before. What is it? This consists of certain 2x2 matrices. So these 2x2 matrices, all of them are upper triangular, meaning in the lower part I have 0. But not all the upper triangular matrices. I have only those ones that have 1 in the lower diagonal corner. And this one is supposed to be non-zero. Otherwise, the determinant of this matrix, which is A, would not be invertible. So A is an arbitrary non-zero real number, and B is an arbitrary real number, and claim is that this is a subgroup of GL2R. So that's the first claim. And remember, GL2R means all the 2x2 invertible matrices. We have discussed that 2x2 invertible matrices under multiplication form a group. Now, inside this group G, I can consider those matrices where both the entries on the diagonal are 1. I have no restriction on the 1-2 entry. So B can be an arbitrary real number, but the other entries are fixed, and it is of this form. And claim is that this subgroup, that I'm going to call it N, is a normal subgroup of G. Moreover, the factor group of G by N is isomorphic to the group of non-zero real numbers under multiplication, the group of units of real numbers. So that's the claim of this example. Let's start by proving why G is a subgroup of GL2R. We are going to use the subgroup criterion in order to show that G is a subgroup. So we need to argue why it is not empty. That's easy, but nevertheless, let's argue why it has the neutral element of GL2R, and that is the identity matrix. That is rather clear because the identity matrix has 0 in the 2, 1 entry, and it has 1 in 2, 2 entry. Therefore, it does belong to G. Remember, this is also non-zero. So, because identity is inside G, it is not empty. Next, I'm going to argue that inverse of every element of G is still inside G. Now, that means I need to find inverse of an element of the group G. There is this general rule that inverse of a 2 by 2 matrix given by the entries x11, x12, x21, x22 can be computed like this. We simply multiply by the inverse of determinant and switch the order of the elements on the diagonal and multiply by 1 the off-diagonal entries. So I get x sub 2, 2, x sub 1, 1, flipping the entries on the diagonal, and then multiplying the 1, 2, and 2, 1 entries by negative 1. So claim is that we get this equality. Okay, so let's see. Either I can use this claim and write down the inverse of AB01. And as I do so, I end up getting that I have to flip this order and then multiply by determinant inverse, which is 1 over A. So I get A inverse here and 1 over here. Then I have to multiply this guy by negative. It doesn't change the fact that it is 0. And then I need to multiply this guy by negative and multiply by 1 over determinant. So altogether, we get that inverse of this matrix is equal to this matrix. And as you can see, it does belong to the group G, because this entry is 0, this entry is 1, and this entry is not 0. But let's actually do it concretely by multiplying the matrix AB01 by the matrix that I'm claiming is the inverse of this matrix, and check whether or not we get identity. So as I simply multiply these two matrices, I need to multiply the first row by the first column, put it over here. A times A inverse is 1, B times 0 is 0, so I get 1 in this component. This times this, A times this is negative B, plus B times this, that one is B, they cancel each other, I get 0. 0, 1 times this, 0 times A inverse is 0, 1 times 0 is 0, I add them up and I get 0. This times this, 0 times this is 0, 1 times this is 1, I end up getting 1, and that's the identity matrix. Therefore, this is indeed inverse of the matrix AB01. That gives us first claim, and in particular, I get that inverse of every element of the set G belongs to the set G. Next, I'm going to argue that the set G is closed under multiplication. So if I give you two elements inside this set, as I multiply them, let's see what we get. I multiply this by this. I end up getting A times A prime plus B times 0. B times 0 is 0, so I end up getting A times A prime. AB times B prime is 1. A times B prime plus B times 1 plus B. Now 0 times 0, 1 times this, 0 times A prime, 0. 1 times 0 is 0, so I get 0. 0, 1 times this, 0 times B prime is 0, plus 1 times 1, I end up getting 1. As you can see, this corner is 0, 2, 2 position is 1, and 1, 1 position is not 0. Remember, A and A prime are not 0, therefore A prime is not 0 either. Altogether, we get that this is another element of the set G. Now, if I give you two arbitrary elements of the set G, Y inverse is still inside the set G, and therefore product of X and Y inverse is still inside the set G. That shows that G is a subgroup of 2 by 2 invertible matrices. So this shows that G is a subgroup. Now let's see, I have to prove the second part. Instead of showing that N is a normal subgroup separately and then trying to argue why we have this, I'm going to use the general recipe. I want to show that this quotient is isomorphic to some other group. I start with a numerator and define a groupomorphism to the other side and hope that kernel of this map that I'm defining is N. If it is N, then for sure N is a normal subgroup of G, and I can use the first isomorphism theorem to understand G over N. So that's the idea. But let's look at this. Let's go back here. So I am asking myself, can I come up with some groupomorphism so that the kernel of that groupomorphism is N? Now, what is N about? N consists of every element here where A is 1. Okay, so the condition is A is 1, and I want to put it inside the kernel of something. Maybe I have to only consider A. Maybe I should send this matrix to the real number A, and notice that this real number A is non-zero. So I'm going to send this matrix to A and get a function from G to non-zero real numbers. Is that a groupomorphism from G to non-zero real numbers? What does that mean? I need to multiply two matrices inside G and ask myself, what is the new 1-1 component? As you can see, the 1-1 component gets multiplied. So we are in good business. So let's see. I am going to define F from G to non-zero real numbers to be the following function. When I feed it an element of the group G, that means when I give it this matrix A, B, 0, 1, it gives me A. It gives me the 1-1 component. By the computation that we have done, we know that when I apply F to the product of these two matrices, I have to multiply the matrices. I do so, and I get this. Then I need to apply F to this matrix. And when I apply F to an element of the group, it gives me the 1-1 component. So it should give me the 1-1 component, that is A times A prime. And A is precisely F of the first element, and A prime is F of the next element. So I get that this is product of F of the first element and F of the second element. That means F is a groupomorphism. So we got a groupomorphism from G to set of non-zero real numbers. Now, an element belongs to the kernel of F precisely when it is sent to the neutral element of the codomain. Neutral element of this group is 1. So this is supposed to be sent to 1, but F of this element is the 1-1 component. That means this matrix is in the kernel precisely when A is 1. So this is in the kernel exactly when A is 1. So kernel of F consists of matrices of the form 1, B, 0, 1, where B is an arbitrary real number. And that's exactly N. That means kernel of F is equal to N, and therefore N is a normal subgroup of G. So in an indirect way, we showed that N is a normal subgroup by finding a groupomorphism whose kernel is N. We argued that N is a normal subgroup of G. Okay, so we understand kernel of this groupomorphism. How about its image? I give you an arbitrary non-zero real number. Yeah, you just pick this diagonal matrix, and F of this diagonal matrix is the 1-1 entry, and that is A. That means every non-zero real number is in the image of F. So image of F is the entire set of non-zero real numbers. Now I'm in a good place to use the first isomorphism theorem. By the first isomorphism theorem, domain over the kernel of groupomorphism is isomorphic to the image of the groupomorphism. Kernel, we showed that is N, and image, we proved to be the entire non-zero real numbers. So we end up getting this isomorphism that the factor group of G by N is isomorphic to the group of units of real numbers, the group of non-zero real numbers under multiplication. So we learned about factor group. We proved the first isomorphism theorem for groups, and we've seen some examples on how to use the first isomorphism theorem to understand the structure of factor groups. Goodbye.